Before I explain a single thing, I want you to watch something. What you are looking at is a language model that I wrote from scratch, in plain code, with no library doing the hard part for me. A few minutes before this, it knew nothing at all, and its output was pure random noise. And then it was trained to do just one thing, which is to guess the next character. Here is what it writes now. Nobody handed it a dictionary, and nobody wrote a single grammar rule. So the real question, the one that we're going to answer together, is how something that began with nothing learns to write. Stay with me, because by the end, you will understand every piece of this and you would have watched it happen. And really quickly, if actually understanding the technology you use every day is your idea of a good time, then this channel is built for exactly that. So go ahead and subscribe, and the full code is linked in the description so that you can build it right along with me. So let us answer it. Everything that model just did comes down to a single task repeated over and over, which is predicting the next token. And a token for us is simply one character, so that every number stays on screen. At each step, the model outputs a score for every possible next character. We call these the logits, and the softmax turns those scores into a probability distribution, and training just means pushing the probability of the true next character as high as it can go, which is exactly minimizing the cross entropy. The simplest model that does this is a bigram, and it is worth 1 minute because it makes the whole idea concrete. We keep one row of logits per character, so predicting the next character is a single lookup and a softmax, and you can already train it and watch the loss fall. But it only ever sees the one current character, so it can learn that a Q is followed by a U and nothing more. And holding on to that single limitation matters, because everything we build after this exists to fix exactly that. And remember, every piece we add exists for one reason, which is to guess the next token a little better, because that guessing is what becomes writing. The first real idea is to stop treating a token as an isolated symbol and give it a vector instead, using an embedding matrix that holds one learned row per token. So a lookup just selects a row. These rows are parameters, so gradient descent learns them. And overtraining tokens that behave alike drift close together, which means a similarity becomes geometry. And that geometry is exactly what will let the model treat related characters in related ways when it is guessing what comes next. If you saw the recommended video, this is the same idea as taste being direction, only now it is meaning. There is one catch, because the attention step we are about to build treats its input as a set. So on its own, it does not know what comes first, and we fix that by adding a positional vector, one per slot, to each token vector, which stamps order back in. After this, a short piece of text is a small stack of vectors, each one carrying what the token is and where it sits, and that stack is what flows into the heart of the model. To guess the next token well, each position needs to pull in information from the earlier tokens that actually matter to it, and different positions care about different parts of the past. So we want a mechanism that for every position looks back, decides how relevant each earlier token is, and blends them. And we want that blend to be learned and differentiable. That mechanism is self-attention. From each token vector, we build 3 vectors with 3 learned matrices, and we call them the query, the key, and the value. The clean way to picture it is a soft lookup, where the query is what this position is looking for. The key is what each position advertises, and the value is what it hands over if it is chosen. And the relevance of one position to another is just the dot product of a query with a key. So aligned directions score high. We score every query against every key. Divide by the square root of the key dimension so the softmax does not saturate. And because this reads left to right, we apply a causal mask that forbids looking at future tokens. A softmax across each row turns the scores into weights that are positive and sum to 1. And the output at each position is the weighted sum of the values. And this right here is the exact moment the model finally uses context, which is the one thing the bigram at the start could never do. And if that idea just clicked into place for you, a quick tap at the like button honestly helps more people find this. And then let us keep going. Let us take one quick breath and see how far we have come, because words are vectors now, and attention lets every position look back at the ones that matter, which is the very thing the simple model at the start could not do. We are only 2 steps from the finish, and those 2 steps are where the random noise you saw at the very beginning turns into real sentences. So stay with me. And while we are here, I'm genuinely curious. So tell me down in the comments, what is the very first thing you would want a little model like this to learn to write? I do read them. Attention lets positions share information, and then each position does some private processing on its own through a small feed-forward network, which is 2 linear layers with a non-linearity between them. And we wrap both attention and this network in residual connections, meaning we add each step's output back onto its input so the gradients flow cleanly. Real models also add layer normalization and stack this block many times, and our tiny version uses one clean block so nothing is hidden. Finally, we take the processed vector at each position and multiply by one more matrix to turn it back into logits over the vocabulary, ready for the same softmax and cross entropy we opened with. And if you step back, the whole forward pass is a chain of matrix multiplication with a couple of softmaxes and non-linearities threaded through, which is why people say a transformer is mostly matrix multiplication. And they are basically right. Now for the part that actually creates the ability, which is training. Every weight we introduce to start as small random numbers, so at first the predictions are basically uniform noise, exactly like the gibberish from the cold open. And we measure how wrong it is with the average cross entropy across every position, which is the same as maximizing the likelihood of the real text. And if you exponentiate that loss, you get perplexity, the number usually reported for language models. To improve, we need the gradient of that loss with respect to every parameter, and we get it by back propagation, which is the chain rule applied carefully backward through the whole forward pass. And in the code, I derive the gradient through the softmax, through the attention weighing, and through each projection by hand, and then checked it against finite differences, because if you are going to say you built it from scratch, the backward pass is the part you should be able to defend. With the gradient in hand, learning is gradient descent, which means taking a small step from every parameter in the direction that lowers the loss and repeating. And while plain stochastic gradient descent works, momentum pushes through flat regions with a running average. The Adam goes further by keeping an adaptive step size for each parameter. And when you run the same tiny model with all 3, the gap is stuck because Adam reaches a low loss far faster, which is exactly the controlled comparison that turns this code base into a paper. So let's run it for real. We start from those random weights, the loss begins high, and as gradient descent does its work, the loss fails and the samples sharpen from noise into structure. And that sentence from the very first second of this video, the one that felt like a magic trick, is simply what falls out of a model trained only to guess the next character. Nobody wrote a grammar rule and nobody gave it a dictionary. It found words, spacing, and sentence shape purely from the pressure to predict the next character well. Before we finish, this was the second video in a series where we build modern AI from scratch, one piece at a time, and the next one takes on the engine underneath all of it, which is gradient descent itself. So if you want to be there when it lands, go ahead and subscribe. A production language model is the same recipe. Next, token prediction, attention, and gradient descent, scaled to billions of parameters and trillions of tokens. And most of what feels magical is what emerges when you scale that one simple objective enormously. But the machine underneath is the machine you just built. It is not magic, and it is not memorizing the internet word for word. It is a differentiable function shaped by optimization to predict what comes next. And once you have built the small one with your own hands, the large one is no longer a mystery. And if you have not seen it yet, the very first video in this series, where we build the recommendation engine that quietly decides what you watch next, is right here on the screen. So go and enjoy it.